My name's Rick Wheeler. I'm actually not somebody who does anything useful anymore, but I've been working on file systems since about 1982 or so, back when storage had to know about how fast your disk spun so you could figure out how long to wait before you tried to write again. So what I'm going to talk about today actually I think is very relevant to Gluster because we're both a consumer of storage and we provide storage for other people. So a lot of what we do in the community, what we do for clients and what we want to consume as a client of other storage layers depends on standards and work done by the kernel. I think Gluster's been pretty good and pretty agile at writing on top of stacks, which actually makes us able to take advantage of other people's work. So one thing I wanted to say is this isn't really a lecture so much. Feel free to shout out, correct me. It's okay to say liar at any point, as you see in my theme. It's something I think storage people do a lot. Whatever we say we do for people who are our clients, we're typically lying, right? So I'm going to talk a little bit about hardware trends, new features in storage standards and system calls from the kernel. I'm not going to go into a lot of technical detail because, again, I'm happy to talk to people offline, but some of this will just make us faster. It'll make us faster if we consume it from the kernel. It'll make our users faster if we provide these hooks to them. So, first of all, as I said, I think we do really well in Gluster at actually consuming the stack as it was meant to be consumed as an application, right? If you can get work for free, we don't have to re-implement it, it's fantastic, right? You save a lot of time and a lot of headache. It can be really complicated and confusing though, because as I said, people argue about this stuff for a decade. I've been, for most of my career at Red Hat, I managed the Linux kernel team that did file systems and storage. We spent most of the last 10 years arguing about giving hints from applications down to storage devices. I don't think almost any of those hints ever existed, right? We're still arguing about what hints there should be and how to do them. Some of them made them. There's also a lot of kinds of new hardware coming in the market today. I'll talk very, very briefly about storage class memory or persistent DRAM. You can actually have those parts today. There are new APIs to use them, or you can just use the existing APIs, maybe run a little slower. We can also use new things that are slower but denser, like shingled magnetic recording drives, SMR drives. And those are also commodity. To use them in a cheaper version, there's probably work that kernel people still have to do. So, first of all, storage class memory. Has anyone heard of this term, persistent memory? So, the cool thing, I'll talk a little bit about this a little bit later, but it has similar performance to DRAM, not quite as fast. It's byte addressable. You don't have to write 512 byte chunks. If you lose power, you'll get most of your data back, right? And when I say most of your data back, it's because when you write it actually, the data goes through your tier of caches, like through the CPU caches. So if you don't use fsync and msync or similar things or special APIs, you could lose like cache stride chunks of data. So you won't lose a whole block, but you might have holes in your data that are kind of odd. But it's actually a new tier. It is actually on the market in some forms today. And importantly, I think, is the cost of these parts, right? The performance cost trade-off will be really interesting to watch. As I mentioned, drive technology, spinning drives, everybody keeps thinking you can ignore spinning drives forever. Most customers still care about really cheap storage. I mean, when they buy storage, they actually buy it based on cost of storing all the data they need, and they want to spend as little money as possible. In my experience in storage, customers usually come in and say a few things. Mostly the first conversation is about, yeah, performance isn't super critical to me, I just need to store this much data. They write you a very small check. You come back 6 months later, they're very unhappy with their performance, right? So they change their mind. Again, this is the theme of lying. But I think what's going to happen is most of us are going to have to deal with tiering of storage. I know Gluster has done tiering. I saw Dan in the back, people who've worked on tiering in Gluster before. Tiering is going to be really common, right? And you'll probably have DRAM like we have today. You'll have storage class memory, you'll have SSDs, and you might even have spinning drives behind those, or even maybe cloud-burst drives, right? And you can't expect our users to manage this. It's something we'll have to manage for them, right? This is just kind of a wild insert hand waving here, but this is the kind of thing that makes us affordable, right? Because you could always say, buy the most expensive hardware you can find and don't use anything else, but it's not practical for most users. Okay, so this is my favorite slide. Like I said, a long time ago, if anybody else here worked on storage in like 1982, raise your hand if you're old enough to remember drives. We used to have these big drives that were about the size of a washing machine, and you'd pick out the platter and you could see all 300 megabytes. It weighed about as much as a small dog, right? Right. In my cell phone, I have orders of magnitude more than that. Well, those drives are big and slow, and the file system actually knew exactly where the head was, right? When you wrote a block of data, we knew how long it took to write, we knew how fast the drive wrote, and so we knew how long we had to wait before we tried to write again. So you did a gap in allocating disk physically because you could figure all that out, and storage really didn't lie to you about 35 years ago. Today, everybody lies, right? When we ask a drive to write for us, it'll say, I'm done. It's not really done. It's probably written in DRAM. If the power goes out, you're not going to get your data back. If you talk to, Jared will talk about some interesting new work that we have in the community called VDO for Device Mapper. When you do DM Thin or you do other software virtualization, your physical layout is really not the same thing that your virtual layout is. So storage people have to get used to thinking, not making assumptions based on what you think the layout is, right? Your blocks, as you write them virtually, are probably not always contiguous physically, and that can have performance implications for us. And to make it even better, you know, as anybody in the Gluster world with translators understands, everything's stackable, right? So we kind of lie to each other all the way down the stack until we get to lie to our users, right? Now, it's not necessarily a bad thing because people shouldn't actually have to care as long as the performance is there and the reliability is there. But it is important for us to understand, you know, how to minimize the amount of pain we have when dealing with storage and how to help storage underneath us be as high performance as best we can. There are some things like generic hints. We'll talk about a few instances of these today. And I think in general, the more information you give to the lower layer of storage, the better off you are, right? If you have to write a gigabyte of data and you write it 16 bytes at a time in a lot of little 16-byte system calls, the storage might do really bad things for you. If you send it the whole gig, it has the most chance, it has the most context to figure out how to place that, how to mirror it, it knows how big the file is going to be. If you go even further and you pre-allocate the file, it knows, hey, this application's got a gig. It's going to be backing a virtual memory image. It's a virtual memory disk file. Excuse me, a virtual machine disk file. So again, the better context we get at the lower layers, the more efficient the storage layers under us can be, I think, in general. And that's true even for people who, again, using my lie theme, who lie to us and say they don't care. Like even SSDs really do prefer not to do billions of small IOs, right? Doing bigger IOs and doing properly aligned IOs is really important for performance. One of the things that's really hard here is, anybody here ever do standards committee work? T10, IETF work? It's painful. It's like watching paint dry. You get together, usually in somewhere nice. You eat lots of nice food. And the most recent one I went to, I think we spent a day and a half talking about which holidays internationally would be recognized when we vote on a proposal, right? This was in Canada, so clearly US holidays weren't enough. It had to be Canadian holidays and there were Indian holidays, and they figured that, eventually they just said, every proposal will take 30 calendar days because they couldn't figure out how to do it in any other language. It's slow, tedious, and in some ways that's a good thing because if you think about it, what we define in a standard, we have to live with forever. NFS, for example, is a good example. NFS v2, NFS v4 as a protocol. It took, a decade, our NFS people here, roughly a decade to get. It's a couple I mean, several hundred pages of spec, and pretty much no one implements it. Not in total, at least. But we do have an opportunity to get involved in these discussions to help drive the standards. When we're talking about storage devices, one of my favorite things is when you do discard commands, things like this, some devices retain the right after you discard a range, saying, okay, I don't need this block at offset 1 megabyte. They retain the right to give you random data, maybe even old data from somebody else, right? Getting involved in the specification, I think the NVMe people did this right. They required you give back 0 data, right? There are codes and bits and bytes in these specs that are really important to this. If you're implementing RAID and you're using discarded regions underneath your RAID device, it's important to discard properly because you can get random junk back sometimes, right? It's kind of a surprise that you could see somebody else's data behind something that is supposed to be empty. And if you don't like going to standards committees, there are people in our community and in the broader open source community who do that. If you have complaints about drives or file systems or NFS, SMB, we can find people that you can complain to and moan to, and they'll moan in turn for us, spare you the pain of going there yourself. But it's important to keep up with this and keep aware of it because it really does control how we access things when we use these kind of legacy industry standard protocols. Just a pointer to a couple of these. Again, T10 is the SCSI one, T13. We don't typically have to worry too much about this. We access things through file systems. I think as a block mode device, we don't particularly care about T10 so much other than maybe as iSCSI initiators, which is mostly hidden from us. SMB, S3, NFS protocols are fairly much defined by vendors. They're not driven by industry standards bodies like IETF, but there are ways to participate in that community as well. And as I said, it does take years to get these things rolling. We have to be vocal about them before they get locked down. Okay, so now on to the fun stuff, right? RefLink. Anybody know what RefLink is? It's a great way to lie to your users, right? Why would you copy a file, right? Praneeth, you have a really important file, you make a copy of it. Why did you make a copy on the same disk? Yeah, so if the first one gets broken, you have another copy, right? Right? So RefLink says, I'll make a copy, but I'm going to use the same blocks for both files, right? So it's a file level copy and write snapshot. The advantage from a server point of view is it's really fast. The disadvantage from a user point of view is that we've lied to you. We haven't allocated any space. You could have a fully allocated file. You look at it, all the blocks are there. As you write it, you're going to start consuming free blocks without even, if you overwrite an existing block in that file, you're going to allocate a new block. So it's kind of confusing. The good use case, though, is again going back to virtual machine images, doing snapshots, copy and write snapshots in something less than a whole, say, LVM device mapper volume. It's actually quite good for us, right? So looking at RefLink as a consumer from file systems, we could implement file per file snapshots or say even subtree snapshots if the subtree doesn't have a lot of files in fairly short time, fairly linear time. And that's actually an important use case for us. Anybody ever talk to customers who wanted that? There's one. Two. Yeah, it's an important use case. Again, and it's fairly constant in time. It's not 0 copy time. I mean, device mapper snapshots are actually fixed pretty much in time. But with with RefLink snapshots, you're just copying the metadata. You're effectively copying the inode in any kind of extents or inode pointers that you have to do. One of the hints that does exist, and we've kind of struggled with this, is pre-allocation. In Gluster, I think we had some issues a couple years back where XFS was aggressively doing us a favor by pre-allocating data beyond the end of the actual written last byte of the file. Anybody recall this work? Yeah, so XFS has this mode where it says, Rick's writing 8K at a time. He's been doing this for hours. I know what he's going to do next. He's going to want more blocks past the end of his file. So I'm not going to change the size of the file, but I'm going to give another megabyte of data at the end of the file, or maybe another 64K or 8K or 10K or whatever, 16K. It's actually a really good optimization because, again, it helps you have a nicely laid out file on disk, even if you do small writes. The problem is if you're doing lots of small files and you pre-allocate a lot, all your files are going to be non-contiguous in those little chunks, and they might not grow. Right, so there's tunables here. You can look at XFS.io for ways to set this per directory. There's ways to tune this. I think Brian Foster, who works at it, he's kind of a hidden XFS kernel engineer in our Red Hat storage team. So he supports the Ceph and Gluster teams as one of our hidden kernel guys. But he worked with us to help tune XFS upstream for this, so it's not so aggressive. And as I said, I think in general, a good pattern is don't write randomly in odd orders. Believe it or not, there are people who do, there's databases that do reverse scans. They start from the last block in the table and read backwards. Right? If you think about that, that kind of foils every optimization anybody underneath you would ever do. It's like, oh, let me read the last block, and then the second to last block, and so on. Right? When I was at EMC, we actually did optimize for that one particular application. Say, oh yes, we found this weird person again. We know it's reading backwards. Right? It actually comes from tapes. fallocate is an interesting system call. Anybody use fallocate? Yeah, so this is pretty cool, right? One of the use cases that you can do with fallocate is you can pre-allocate files. In the most trivial way, again, going back to the lying, you can pre-allocate a 1 gigabyte file by just setting the file size offset to 1 gig. Just write a byte out there. You've allocated exactly 4K of data. Every write you do in the middle of that file is going to randomly allocate a block from somewhere on the physical storage to that file in the worst possible layout that you could ever get. It's hideous, right? There are ways to pre-allocate all the blocks really, but not write them. And there's also ways to pre-allocate the file with the I think it's fallocate 0 range, which will give you the physical write and guarantee that all the data has been zeroed as well. It's interesting to play with this. It's also interesting to think about this as a server for people who might want to do this through block mode for Gluster. Similar for NFS, you can do punch holes, which is, again, we talked about discard, but punch hole is the ability to take a chunk of data out of the middle of a file without having to copy it into a new file, skip past the parts you want to remove, and then keep going. Right, so punch hole is really big in video editing. I think it's also really good for virtual machine storage because you can deallocate big chunks of data that the guest operating system is not using anymore. One thing that people sometimes see with discard, if you've played with discard in Linux before, they'll often say, I did a discard, the consumed amount of blocks in my file system or my storage device didn't actually go down. And why is this? I'm going to go back to my lying theme. It's an optional thing, right? It's actually compliant with the spec to get a discard command and just ignore it. And you do more than ignore it. You can ignore it after you say, yep, I did that. Right? So discard's not always mandatory. It's the storage target device, whether it's a software device or it's a physical device, is allowed to arbitrarily ignore that, typically based on the alignment of the request and the size of the request. Right? So if it's too small, it's not a full block, it'll discard it. If it's not aligned on a region, it'll discard it. So typically what we do is we run something called fstrim, if anyone's used this, which will, say for XFS or ext4, lock a range of a file system, discard as big as the chunks as it can, and then unlock that region, go on to the next region. But again, important to remember that these things are optional. They're not always hard promises. How that behaves depends very much on the storage target. A similar thing that's kind of magic, and you can do this in a lot of different ways, is server copy offload. If you think about copying a virtual machine image file, which is my favorite, I look at our RAI team here, I'm picking on you here, having the biggest, fattest files ever, right? You know, multi-gigabyte files is kind of the smallest you get. If you want to make a new copy over NFS or over Gluster, over Fuse, if you have to read all the bytes to the client and then write all the bytes back to the server, you've done 2 data transfers, when actually you really want to be able to just tell the server, hey, I want a new version of this file over there. Don't give me the bytes, just tell me when you're done, right? You can do this over client-server things. That's what server copy offload is. There's a new system call in 4.5 kernels and beyond, copy file range. It can do it on a whole file or partial file. Yep. Is copy file range sparse file aware? I think that would be entirely up to the implementation of the block layer. I mean, again, it depends. I think optimally it would be, but if you're doing copy file range for a storage device, it could be on a block. I mean, it could be in different implemented differently through NFS or Gluster or XFS or ext4, and it can fall back to actually doing a physical copy, right? I would hope it would skip over unallocated things. But this would be a cool thing for us to do. And by the way, you could do copy file range just in a local disk, and the local disk or file system could offload it to something like a reflink, right? So controlling what it actually does, has it given me physically contiguous blocks or not, or just reused blocks and given me another pointer to them under a different name is actually important. So the implementation details are really critical here, and you'll get surprised in a nasty way if you don't understand how your dependent stack implements them. There is sample code in the man page to look at this and how it falls back. So it's worth having a look. DAX, this is what I mentioned before. Anybody heard of DAX? Some people have. This is the, what do we call it, the direct access, something like that. I think that it was we argued a lot about this name. There's a bunch of stuff. But effectively what this means is, with XFS and ext4, you have a mode with the file systems where you can put on these new storage class memory devices. You can do all the normal stuff through the normal I/O path through a virtual block driver that pretends like you're like a floppy drive or whatever. Or you can map this memory that you have in a file into your address space and touch it directly. As I said, you have to be careful with this. Every write will write to durable domains, but you're writing through CPU caches, multiple layers of caches. Unless those cache lines are fleshed out to the durable domain on the part, it's not going to survive a power outage, and you're going to get a really weird looking file when you come back, right? Because again, the kernel is not in the middle of this. It's just your application and the hardware, effectively. So we give you, what was the Spider-Man quote everybody uses? With great power comes great responsibility. So as an application, you get the entire kernel I/O path out of your way. Fantastic for latencies. You have to worry about everything else, right? So you have to worry that the data is actually going to survive. The biggest vendor in this space today is probably Intel with their, I think it's called Crosspoint. Is that the part name? They are out there. You can get them. You can pretend to have them just by playing with DRAM in DAX mode in persistent. These are trickling to the market. There are some weird things with these parts that we argued with Intel and other vendors about. When you have, say, a terabyte of these parts and you have an I/O error, what happens? Any guesses? If you bought a commodity system, what they do is they reboot your box. So every disk error is effectively terminal to your system. The whole operating system reboots. Some enterprise server class parts actually will survive that in a durable way. But again, the quality of the part and the system controller have a big difference. So that's it. I have, I think, 1 minute left. I got my 2-minute warning. Any questions? Anything you would want us to take back to the kernel team or NFS, SMB teams that we haven't done yet? This was either the easiest crowd or the most boring talk you've heard today. Yeah.
Hey, Rick, thank you. I've been seeing things about DM cache and didn't know if you had any comments about that.
Yeah, DM cache is something we've played with pretty extensively since, again, we have used it, I think in Rye, in the hyperconverged. We use it under our VM machine images when we configure it as a product. Historically, DM cache had some performance issues. I know Dan played with DM cache. Dan, you can wave in the back, before he did his tiering work. But DM cache had some really, it's not really a cache like a write cache on a hard drive. Historically, it had a very slow warm-up. So they've worked hard to give you different caching algorithms. It's worth looking at again and looking at all the different ways they implemented caching. It'll vary whether it helps you or not based on the class of storage device that you're using in this cache, the storage you have behind, and what algorithm you use. But people are working very hard. Joe Thornburg, Mike Snitzer, the device mapper community, very involved in trying to make it more generic.
One thing that would benefit GlusterFS, what I think is some way to get a bulk metadata like XATTRs from the local file systems. So that might benefit better, I guess.
Yeah, so XFS actually does have bulk inode stats, right? So you can do bulk inode stats for XFS. That is file system specific. We can talk, we can take that offline or take it to the Gluster community list. That would be an interesting thing to discuss. But bulk stat is a great application. There was also kernel work to do weird stat operations where you could kind of mask what fields you care about or not, right? Some of them require you can get entirely from disk or not. Things like file type or in directory entries, not having to stat an inode just to see if it's a file or a directory is a good thing for recursion.
Other questions?
Yep, I'm around both days. You can find me anytime. And as I always say, people who work in open source don't hide well. So if you don't have my email address, just Google my name, Rick without a K, Wheeler, and you'll find me.
Great.